Okay, so this video is going to be reviewing titrations, but more specifically looking at back and indirect titrations. So as we know, a titration is where we take volumetric glassware, so for example we've got our burette, and then we've got some sort of unknown solution in our conical flask, and we titrate it against a known concentration of a solution in order to find how many moles of each is needed to reach the endpoint, and then work backwards using our stoichiometry to determine the concentration of that unknown. So the idea is that this is a titration, but it is a direct titration. And it's direct because we are directly working out the concentration of the unknown using the titration, whereas a back or indirect titration isn't quite the same. So in a back and indirect titration, instead here we have an unknown where we can't do the titration as the first step, and that could be for a variety of reasons. It could be that our unknown is too volatile. So volatile means that it reacts very readily or turns into a gas quite readily at room temperature. It could be that it is an insoluble salt, so insoluble in water, which means that we can't make a solution of it. Or it could be that when it undergoes a reaction that we would normally do for a titration, it's too slow. And so we can't do a normal direct titration. And so instead we have to do what's called a back or an indirect titration. They're slightly different, but both are using our stoichiometry and a titration to work out the unknown. We're just doing it in a slightly different way. So let's start with a back titration. So in a back titration, we have two steps. Step one, we add our unknown, so I'm calling this my unknown. We're going to add that, we're going to add some sort of other thing to that in excess. So we're going to add that in excess, and that's going to react to form two different products. Now, the fact that we're adding this in excess means that this is our limiting reagent, and all of this should be completely used up. And so we should get left over a mixture of C and D, but also we'll have B left over, because the idea is then we're going to take our mixture, and our mixture is kind of a mixture of all of this, but really this is the only thing that's going to react in our titration. So we're going to take that B and we're going to react it in a titration with something else, and by doing this we should be able to work out the number of moles that was left over from this original reaction. So in this reaction it used up some, but if we know how much we added originally, then we know how much was left over that reacted in this titration, and we can work backwards in order to find out the concentration of our unknown solution. So for example, let's leave that there. So for example, let's look at if we had a sample of calcium carbonate. So calcium carbonate, which is found in limestone or chalk. So we just had a big chunk of limestone. So it contains calcium carbonate, but we don't know how much. The mass altogether is about, let's just say 1.5 grams altogether, but we don't know how much of that mass is calcium carbonate. And so we want to find out that. However, we can't do a titration with this, obviously, because it's a solid, and so we need to do something to it first. So what we're going to do is we're going to take some hydrochloric acid, and we're going to add that in. But we need to make sure we know exactly how much we add in, and we have to try and make sure that we're adding it in excess. So what I'm going to do is I'm going to use a concentration of about 0.2 molar HCl, and I'm going to add in, let's put in 50 mils just to make sure that it's enough. Oops, sorry, so that's liters. So we're going to add that into calcium carbonate. Now what's going to happen then is that calcium carbonate is going to start to dissolve, and that should hopefully be enough HCl that all completely dissolves and leaves us with a mixture of our products. So in that reaction we have calcium carbonate plus HCl going to calcium chloride plus water. Now that's not balanced, so I need to make sure I balance it so that my mole ratios work out. Should be balanced now. And the idea is that here originally my calcium carbonate had a mass of 1.5 grams. My HCl, I had a concentration of 0.2 moles per liter and a volume of 0.05 liters. Now, so this is my step one. So that's really important. So this is my step one. I'm now going to take that mixture of everything and I'm going to perform a titration with it. So I'm going to get my burette. Because it's HCl, I'm probably going to add some sodium hydroxide to that. Let's make it a concentration of 0.1 molar. And I'm going to put my beaker of my mixture in there and see how much I need in order to get the end point. So I should have a mixture in here of about 0.05 liters, but it doesn't really matter because the idea is we're just finding out the number of moles of sodium hydroxide and then we can work backwards. So let's just say I do that titration and I find that in my sodium hydroxide I needed, let's just say 0.032 liters to reach the end point, which is 32 mils. So that means that I needed that much to neutralize the hydrochloric acid in this mixture, because remember, even though we've got these other products probably in this mixture, it's only really the HCl that's going to react with the sodium hydroxide. So this step 2 reaction, now we're taking HCl, we're adding in sodium hydroxide, and it's going to make sodium chloride and water. Now I don't need to do anything else to that, that's already balanced. But now I know a little bit more information, so I know that my concentration was 0.1 molar, my volume was 0.032 liters, and I want to find out the number of moles of HCl that was left over from that first reaction there. So first we find out our number of moles of sodium hydroxide in step 2. So that's going to be C times V. So that's going to be 0.1 times by 0.032 liters. And that should give me 0.0032 moles. So now, working out how much HCl was left over, so number of moles of HCl in step 2, so this is how much was left over. It's going to be a 1-to-1 ratio, so 1-to-1 mole ratio. Remember, we need to state that. So it's going to be 0.0032 moles also. Now the idea is that left over is telling us that from what we originally added, so this is added, only 0.0032 moles is left over. So now we need to know how many moles we added originally to see how much was actually used up in this whole reaction. So the number of moles of HCl added in step 1 is going to be, let me put there. So from this first reaction, our C times, so C times V is going to be 0.2 moles per liter times by 0.05 liters altogether. Let me just get my calculator. And that gives us 0.01 moles. So what this means is that we originally added in 0.01 moles of HCl, and then when it underwent the reaction, a certain amount was used up, and the amount that was left over was 0.0032 moles. And so now, in order to find out how much HCl was used up altogether, we need to use our HCl added minus HCl left over. So the number of moles of HCl used in step 1 is going to be number of moles of HCl added minus number of moles of HCl left over or excess. And so we said when we added in 0.01 moles and the amount left over was, let me just double check, 0.0032 moles. So the number of moles of HCl used in total is going to be 6.8 times 10 to the negative 3 moles. This means that it took this many moles to completely dissolve all our calcium carbonate. And so now we can do our mole ratio. So looking back at our first equation in step 1, so we can do our mole ratio between the HCl and the calcium carbonate to work out how many moles of calcium carbonate there were in that sample. So the number of moles of calcium carbonate is going to be half the amount of the number of moles of hydrochloric acid used, because it's a 2-to-1 ratio, so twice as much hydrochloric acid compared to calcium carbonate. So it's going to be, a half times 6.8 times 10 to the negative 3 moles, which is 3.4 times 10 to the negative 3 moles. So that means I have this many moles of calcium carbonate in my sample. Now, the sample was originally 1.5 grams, so if I want to know how much of that, what percentage of that was calcium carbonate, I'm going to need to know how much mass of calcium carbonate I have in that number of moles. So in order to do that, mass is going to be number of moles times molar mass. So I know my moles is 3.4 times 10 to the negative 3. So times that by my molar mass. Now my molar mass of calcium carbonate, I'll just work that out. Let me put it over here. So mass, calcium carbonate. So calcium is, there's my periodic table. So 40.08, carbon is 12.01, and 3 lots of oxygen. And so that's 100.09 grams per mole altogether. So going back to our calculation of how much mass of calcium carbonate we have, it's going to be 3.4 times 10 to the negative 3 times by 100.09 grams per mole. I haven't left myself very much space. So when we go to work that out, the mass of calcium carbonate in the sample will be 3.4 times 10 to the negative 3 times by 100.09, which is 0.340 grams. Just going to 3 significant figures there. Now, if originally we had 1.5 grams of, what did we say it was, limestone or whatever calcium carbonate containing thing it is, then the percentage of calcium carbonate in there is going to be 0.340 divided by 1.5 times 100, and so that works out to be 22.69%. So that's using an example of a back titration. So just to recap what we did. So we had a sample of calcium carbonate, we reacted it, or we dissolved it with some acid, and then took that mixture and did a titration in order to determine how many moles of HCl was left over. So we had to add that in excess, and when we knew how much was left over, we could work out how much was actually used in the reaction, because we know how much we added, and so then we could work backwards to say, okay, there must be this much amount of moles of calcium carbonate, therefore this much amount of mass. So another example we're going to look at is indirect titration. So while a back titration is working backwards, an indirect titration is slightly different. Indirect titration. So for example, with this one, we're going to take, in our step 1, we're going to have some sort of unknown A. We're still going to add in some sort of other thing in excess. We have to do that. However, then what we're going to do, oops, sorry, that should be a big arrow. So then what we're going to do is we're going to take the product that is produced and do a titration with that. So the idea is that if we've added enough of this in excess, A is still our limiting reagent, and so it's limited how much C is produced, and we take that C, or the amount of C produced, and we put that into a titration reaction, and then work out how much C there is left over here, or that was made originally. So an example of this is if we take, let's just say, a sample of air, not just any air, but air that contains a sample of polluted air. Can't really see the air, but it's got some pollutants in there. And we want to work out how much ozone is in that sample. Now let's just say we have a 30 litre sample of air, and we took a beaker which has an excess amount of iodide ions. So it doesn't really matter at this point how much, what the concentration or volume is. The point is it's in excess, and we're going to bubble that air into there. So that's going to bubble in there. It's going to react, and through that reaction, we're going to get iodide produced. So that reaction can be written as O3 plus iodide, and we usually do this under acidic conditions, and it produces oxygen gas plus iodine and water. Now that's not balanced as it is, we need to add that in, but the idea is once we've done this reaction, so before we couldn't do a titration with that because it's just gas, but now we're getting this iodine produced, and iodine produced, and the iodine we can do a titration with. So that was our step one. So I'll leave that there, step one, because what we're going to do next in our step two is we're going to take our sample and we're going to titrate it. So this must have a lot of air in it because it was 30 liters, and we're going to titrate it against thiosulfate ions. Normally found as sodium thiosulfate, but we don't really care about the sodium thiosulfate. And in there, it's going to react with the iodine. Now that reaction of thiosulfate with iodine looks like this. So I'll balance it already because I've got one prepared here. So iodine turns into S4O6, 2 minus plus 2I minus. And so if we know the concentration of this thiosulfate and we do a titration to see how much volume is needed, we can then work out how many moles of I2 is present here, so how many moles was made through this reaction, and then we can indirectly tell how much ozone we had. So if we do this titration, we have a concentration of 2 times 10 to the negative 3 moles per liter, a volume, let's just say the titration took 17.84 mils. I know that's not in liters, but I'll convert it in a sec. So first thing we need to do is work out the number of moles of thiosulfate used in the reaction. So number of moles of thiosulfate, it's going to be C times V, so it's going to be 2 times 10 to the negative 3 times by 0.0174 liters. So if I do that calculation, so that gives me 3.568 times 10 to the negative 5 moles. And then after doing that, I do my mole ratio between sodium thiosulfate and iodine. So number of moles of iodine in step 2 is going to be, because it's a 2-to-1 ratio, 1 on 2 times the number of moles of thiosulfate ions. If you're still not sure how to get the mole ratio from here, ask me and we can go through that separately. So it's going to be a half times the number of moles we calculated here, so 3.568 times 10 to the negative 5 moles. So that is 1.784 times 10 to the negative 5 moles. And so the idea is that because we took everything that was made here and went and reacted it in our titration, all the number of moles of iodine that we've calculated here that was inside this mixture should be the number of moles of iodine that was produced in step 1. So really the number of moles of iodine in step 1 will equal the number of moles of iodine in step 2. So the number of moles of iodine in step 1 should also be 1.784 times 10 to the negative 5 moles. So that's good, but still not quite getting us to where we want, because we want to find out how much ozone we've got. However, now we know the relationship between ozone and I2, so it's still a 1-to-1 ratio. So let's get rid of that. So now the number of moles of ozone that was made in step 1 is going to be equal to the number of moles of I2 in step 1, because it's a 1-to-1 mole ratio. So the number of moles of ozone should also be 1.784 times 10 to the negative 5 moles. Now the question was originally how much of that sac of air was ozone. Can't see it, just saying how much was ozone. And so we want to work out the concentration of ozone in that thing of air, and so concentration, as we know, is going to be N on V. We know the number of moles, and we said that we had 30 liters of this to start with, so the concentration is going to be 1.784 times 10 to the negative 5 divided by 30, and if we do that, we should get 5.95 times 10 to the negative 7 moles per liter, going to about 3 sig figs. So just going back to what we did. So in step 1 we took a sample of air and we wanted to work out the concentration of ozone in that sac of air. We bubbled it into a solution of iodide ions and making sure that was in excess, so that there was some left over, or at least all the O3 was used up. That O3 all got used up, so we tried to work out the amount of I2 produced by taking that whole mixture and doing a titration with it. And so we did a titration with a known concentration of sodium thiosulfate, and after working out how much sodium thiosulfate was used, we could backtrack and indirectly work out the amount of ozone produced. Okay, thank you for watching, and we'll go through some more stuff next week.